Hi, I'm Ilia. I'm going to talk about the Sanctum project at MIT, which I did jointly with Victor Kostin, who's now at Google, actually, and Srini Devadas, who I think can't be here today, but might be here tomorrow. So let's get right into it. I guess I should also say that throughout this talk, I will use colors in a consistent way. The yellow blocks, which are at the bottom of this diagram, are authenticated trusted software, whereas the blue blocks are unconditionally trusted blocks, such as your Intel processor today. So if you'd like to compute remotely today, what you end up having to do is you package your code and your data and you ship it off to something like Amazon's EC2, where you will trust everything with greater privileges than your code, simply because everything with greater privileges than your code will have more access to the machine than your code will. So that is the story for today. Even though operating systems and hypervisors and system software in general attempts to present this isolated view of the machine to everything with lower privilege than itself, the size of the trusted code base is quite ridiculous. So not even discussing the size of the microcode in a typical Intel chip, if you consider the size of a hypervisor today, the Zen hypervisor, for example, weighs in at about 150,000 lines of code, and we all know that more code means more security vulnerabilities, and the Zen hypervisor reports about 40 security-relevant bugs per year today. Now, the story gets weirder when you talk about the operating system, which weighs in, Linux weighs in at about 12 million lines of code today, device drivers and all, and any sane security engineer should not be considering this a part of the trusted computing base. It's insane that we do in the context of remote computation in the cloud. Sanctum, our project, will attempt to decouple the notion of privilege from the notion of trust, allowing you to reduce the trusted computing base in software just to the applications you care about and a small amount of relevant code. So, but that's not the end of the story here, because there's a growing body of academic work that demonstrates that the isolation boundaries presented by system software are not always meaningful. Operating systems attempt to separate processes, and hypervisors attempt to isolate guest operating systems. But a credit card will get me co-located with some poor victim on a cloud, no problem. And being a sketchy individual, I could launch some malicious attack that attempts to observe the victim's use of the shared resources, like the processor, functional blocks, the caches, the networks, the shared data structures in the hypervisor needed to get the guest operating systems to run, and so on. And all of this sharing will leak private information. There's a growing body of academic attacks that defeats pretty much every crypto system known to man through arbitrary kinds of sharing, like in this diagram. So Sanctum will use a hardware-assisted isolation primitive that will create stronger isolation guarantees, preventing entire surfaces from being used for these kinds of attacks. I will discuss at length at the end of this talk how ours works. Our work lives in this general domain of remotely attested execution. And the high-level idea here is you end up trusting some piece of hardware at a remote machine. And this remote trusted hardware will act as a witness, which will cryptographically measure and produce a certificate for the entire software ecosystem that lies in your trusted computing base. So with its private key, this trusted hardware will produce a certificate that will convince a remote user that this software ecosystem is indeed trustworthy. Once the remote user is able to make a binary distinction between a trusted system and an untrusted one, they can ship their private data and their computation into this environment, having reasonable guarantees that their code has privacy and integrity guarantees. This is a fairly old, well-studied, high-level idea, and of course the devil is in the details. And there's been lots and lots of work trying to implement systems that look like this in the past, and I'm not going to go into details, but essentially they all fail for two different reasons. First of all, they're unable to protect their own cryptographic keys, and an adversary that's able to steal the private identity of a machine is able to impersonate it via an emulation attack. An emulation attack allows an adversary to build a machine that looks to you, the remote user, just like the one you're trying to actually use, but does not offer any of the guarantees that are relevant for security. The other problem with prior work is that the attestations, the certificates that this trusted hardware has produced, cover entirely too much software. If you, the remote user, receive a certificate that says, hey, this TPM module measured the entire 12 million lines of code that was loaded into a remote computer, do you trust it, yes or no? Your answer should never be yes, because code is buggy. So enter a more recent work. Many of you may have heard of Intel's SGX. And these guys did a lot of things right. They built a microcoded, essentially hardware primitive that allowed an unprivileged process to be isolated from system software. They created this notion of an enclave, which is an isolation container surrounding one process that enables the memory and the compute of that process to remain resistant to spying by compromised system software. This is a really good idea because it allows you to remove from your trusted computing base the ridiculous bloat of system software that is necessary for efficient scheduling and such, while still trusting only the code that you actually need to trust in order to do your business logic. So unfortunately, the devil's in the details, and none of these security arguments make any sense without considering the threat model. And here's where things get weird with Intel's SGX. SGX attempts to protect the integrity and privacy of a thread of a process against a compromised operating system or hypervisor. This they do well, but they mostly only consider attacks dealing with direct reads and writes to the enclave's memory, modifying or reading or writing the device registers, or configuring attached devices to steal private information through DMA. These are the same kind of protection mechanisms an OS enforces, and they simply elevated the enforcement of some of these protections into microcode, which is considered a part of the Intel's trusted computing base. They also protect against some very specific physical access attacks. They aggressively encrypt enclave memory and DRAM. They also obfuscate storage of device private keys in the fuses on chip. They don't, however, consider any attacks that involve shared resource observation. And there's a lot of attacks already since the announcement of SGX that demonstrate that you can steal quite a bit of private information simply by observing things like dirty bits and page tables, which are indeed visible to the potentially malicious operating system. We haven't even discussed in this slide what can happen with things like cache timing attacks, which are increasingly prevalent in terms of academic work. And of course, in the context of remotely attested execution, privacy is integrity because these machines must be able to protect their own cryptographic keys. Now, I'm pretty sure nobody's actually seen a production launch enclave from Intel's SGX. We'll see whether or not they're able to protect their keys, but we sort of took a slightly different approach. In Sanctum, our threat model protects against the usual direct attacks, just like Intel's SGX does, but we also consider a great number of side channel-like attacks conducted by potentially malicious operating systems. Our attempt was to create an easy-to-communicate threat model. Essentially, what we want to do is we want to present the abstraction of a protected private process with integrity guarantees. If you run your secret code inside of this process, inside of this enclave, then it is resilient to an arbitrary software adversary. Of course, this being academic work, we have to be rigorous, so we protect the following surfaces. We protect the caches, we protect microarchitectural state, we protect data structures which must exist in order for a process to run on a physical machine, and we also protect events like interrupts and faults. We offer no protection in Sanctum against fault injection attacks like rowhammer because we simply must trust the hardware as built by the manufacturer is indeed correct and not buggy. And we do not protect against physical attacks because once an adversary has been able to touch your machine, it's very difficult to convince the adversary to perform only the specific attacks that you protected against. So to do this, Sanctum places the manufacturer in the role of a certificate authority, just like we have on the web with HTTPS. So the manufacturer not only is responsible for correctly implementing Sanctum, which is RISC-V plus some extensions, but also to endow each device they make with a unique cryptographic key pair. With their public key, they produce a certificate for each of the devices they've manufactured, and this certificate should be enough to convince a remote party, you attempting to compute in Amazon, that the machine you're communicating with is indeed a trusted Sanctum machine produced by a manufacturer that you trust. We also introduced a security monitor, which runs in machine mode and correctly configures and maintains the security invariants that a Sanctum machine needs in order to enforce their privacy and integrity guarantees for enclaves. The security monitor in turn boots commodity operating system, which can launch processes, and so on. There could also be a hypervisor in this picture, but it's a slide, so I kept it short. And finally, when an operating system wishes to launch a secure enclave, they will ask the security monitor to produce an isolation container with a specific set of data and produce an attestation for that secure enclave. This means that the security monitor will use its keys produced by the Sanctum hardware, endorsed by the manufacturer, to produce a hash and a certificate for that hash for the specific program loaded inside of an enclave. Presented to a remote user, this last certificate is enough to convince them that this is a specific body of code loaded into a specifically configured enclave run by a specific security monitor on a piece of hardware that was manufactured by a trusted manufacturer. This is a chain of custody through this one certificate that goes all the way back to the manufacturer, which is very important in the context of remote computation. Sanctums, just like Intel SGX, we bypass the need to include the bulky operating system software and other system software into the trusted computing base, and we include, besides the contents of the enclave, only the 5,000 or so line of code security monitor. This is designed with formal verification in mind, and although it is replaceable by the machine owner, it will be authenticated and will be presented to the remote user as part of the attestation. This allows security vulnerabilities to be patched out of security monitors in a realistic setting. Unlike SGX, we also present a stronger isolation primitive. As discussed in the threat model slide, we protect against a broad range of indirect attacks in addition to the direct memory manipulation attacks earlier. I will dedicate the rest of this talk to showing you how those work. So Sanctum modifies the Rocket Chip produced by the fine people at Berkeley. And our design philosophy was to build just enough hardware support to enable the security monitor to do its job, namely to enforce the security invariants needed by Sanctum. We're not interested in convincing you that we didn't break any of Rocket Chip. So to that end, we only implemented a few gates here and there in order to add invariant checking logic between the large function blocks of Rocket Chip. Nothing that we did is terribly specific to Rocket Chip and should translate fairly well to any system that looks like it. Although if you consider a larger, say, out-of-order system, then there may be more shared surfaces that could leak private data that would require additional consideration. Our approach in securing Sanctum was to explicitly multiplex private state from the global domain. Essentially, an enclave will receive a private and permanent allocation of all of the states that it needs to perform its duties until the operating system or the enclave itself wishes to terminate. So first and foremost, enclaves will receive private cores. An enclave will never share a core with a potentially malicious entity, and as part of its core allocation, it will also receive a private TLB, a private page table history, a private branch history, and private registers, and the private caches. The security monitor is tasked with properly sanitizing all of these structures anytime an enclave is scheduled or descheduled from a core. Of course, since Rocket Chip does not have simultaneous multi-threading, this story is a little bit simpler than it would be on something like an Intel chip. Sanctum also must isolate physical memory that belongs to enclaves from everything else in the system. So we define a unit of isolated memory as a DRAM region. This is a term that we've coined. And we maintain the invariant that an enclave must only use its own DRAM regions for storing its private data. And the machine will maintain the invariant that the DRAM regions belonging to an enclave belong to it exclusively. A potentially malicious operating system may not access an enclave's DRAM regions. This is a high-level statement, and I will refine it in future slides. You may also notice on this slide that I've placed the enclave page tables into the enclave's DRAM region. This means that an enclave will receive a private data structure to manage its own DRAM region. An operating system will not be able to spy on or modify the page tables that an enclave uses to touch its own private memory. Again, more on that in a few slides. So let's discuss how we isolate things in the last level cache. This is a shared structure that is used by all the cores, and it's necessary for performance, so we better get this right. A last level cache, a very typical one. So in Rocket Chip, we use a set associative last level cache, and the physical address, when used to look it up in the cache, is broken up into 3-bit fields. The middle bits in this cache are the set index, and these determine exactly which locations in the cache data structure are used to store a specific address. While an application is running, a specific set in the cache, a specific address, may compete with other software. A motivated attacker, especially a privileged one, can create some pressure on a specific set in the last level cache and can measure the availability of its own data that competes in the last level cache with that of the victims. Through this fine-grained measurement of availability of the last level cache sets, they can learn some private information about what the victim workload is doing. So our solution in Sanctum is to give private cache sets to an enclave. That's, of course, easier said than done, but we use an address translation trick. Here's how it works. Remember that when translating virtual addresses to physical addresses, the lower 12 bits of the address are not translated, giving an application full control over what happens to the bottom 12 bits of the address. The top bits, however, undergo translation, which is controlled by the page tables, which are in turn controlled by a potentially malicious operating system. So we consider the top 20 bits of a physical address untrusted. This is the same physical address that's used to look things up in the cache, and when you put them side by side, you see that there's some overlap between the physical page number bits and the set index. In the context of our prototype machine on Sanctum, we have 6 bits that are untrusted in the set index. Our idea here is that if we maintain the invariant that an enclave receives an allocation of all possible physical addresses with a given set of those 5 bits, then it must follow that an adversary will not have any addresses available with which to mount a cache timing attack on the LLC. Here's how this works illustrated. If you assign a hue to each of the possible combination of those 5 bits, and in this case, I use a toy example with only 3 bits of DRAM region or color, you will see that if you plot all of your physical memory linearly from low addresses to high addresses, you will see contiguous blocks of color, each one of them 1 page precisely in size, repeating every 8 pages. If an enclave receives an exclusive allocation of all of the red pages, then an operating system which may be malicious will not be able to create an address that will compete with any of these red pages in the last level cache, and therefore will not be able to exert pressure in the last level cache on the enclave. This is sufficient to isolate addresses. This is sufficient to isolate enclaves from the rest of the system software in the machine. However, it poses a bit of a problem. In the real world, we need to allocate large DMA buffers to communicate with devices. And in this toy example, with only 3 DRAM region bits, even a 3 kilobyte block will span all of the available colors on the system, leaving absolutely no room for a private allocation to enclaves. So although it's not critical to Sanctum's security properties, we observe that if we simply shift the physical page number bits one to the right before looking it up in the LLC, it will double the contiguous length of a color in physical memory. We can keep doing this until until DRAM is divided into contiguous chunks of a single color. This only impacts cache translation, which also does impact slightly the locality of how your LLC is used. But this also allows you to easily allocate large DMA buffers without clobbering the entire available set of colors in your system. All right, so I talked a lot about this idea of giving private things to enclaves, and here's where we actually get into the implementation of how it works. We take advantage of the fact that all virtual address translations in Rocket Chip go through the TLB, and if the TLB does not have an entry you're interested in, the page table walker, a finely optimized state machine, will fetch the appropriate virtual to physical address mapping from the page tables from main memory. We interpose on the interface between the page table walker and the memory subsystem and examine the page table entries that it fetches. We add some invariant checking circuitry onto this interface, and whenever a page table entry is fetched that looks to be violating Sanctum's security properties, we lower the valid bit of that page table entry, causing the machine to go into false state. This will force the security monitor, which runs at machine mode, to intervene and handle whatever just happened. We use this mechanism combined with the assumption that all TLB entries currently in the TLB adhere to Sanctum security policies. By induction, if the TLB only contains legal entries and no new illegal entries can be added to it, we're good. Assuming, of course, the security monitor properly sanitizes the TLB when the security policy of the system changes. Here's how we use this mechanism in order to protect the security monitor's memory from everything else in the system. If we were to not do this, an attacker could read out the private keys from the security monitor, or it could, and therefore emulate it, or it could simply inject some malicious code into the security monitor's memory, allowing it to do arbitrarily bad things. We create a pair of new registers, machine mode registers, the protected range base and mask registers that define a section of physical memory as off limits for virtual address translation. Since the security monitor is the only piece of software running in machine mode on the system at any one time, it must follow that it is the only thing that can access memory directly, bypassing this requirement for all addresses to lie outside of the protected range. We also use the same mechanism to isolate enclave memory from other memory in the system. We define a new machine mode register called the DRAM bitmap register, which for every DRAM region in the system gives a core a permission bit. A core with a specific DRAM region's bit set to 0 will not be able to create a translation from a virtual address to a physical address that maps into that specific region. By properly maintaining this register across scheduling and descheduling of enclaves, the security monitor can allow this machine to enforce physical memory isolation on a Sanctum machine. This, of course, simply by allocating things at DRAM region granularity also means that enclaves will receive private LLC sets. The final hardware trick that I haven't talked about yet is, of course, what to do about the operating system's ability to spy on an enclave via its page tables. We define a pair of new registers called the enclave virtual base and mask register, designating a range of virtual addresses for an enclave as containing only private memory. So if a virtual address falls into the enclave virtual range, as per this circuit on top, then we will use a private page table. And to do this, we will replicate all of the registers that I've mentioned in the previous slide and have the security monitor properly manage and populate the entries in the enclave private page tables. We essentially duplicate page tables, DRAM region bitmap registers, and the protected address range registers in order to give an enclave a private configuration for the virtual addresses that are deemed private. If we were to not do this, an operating system could spy on an enclave via observing the dirty bits in its page tables, or it could perhaps remap page table entries to unprotected memory after attestation has been achieved. To do all of this, Sanctum modifies Rocket Chip, as I've said before. And again, we're not interested in convincing you guys that we didn't make any mistakes. So we implemented as little hardware as we could, which is great because I'm just one grad student. So we interposed on the interface between the page table walker and the cache subsystem in order to implement the invariant checking circuitry that I showed you in the previous 3 slides. This is quite small indeed. In our FPGA prototype, this is about 500 gates and a few hundred flip-flops for all of the various configuration registers that are required. We also added the last level cache address rotation circuit, which allows you to coalesce the DRAM region, the DRAM regions in DRAM into a contiguous. Okay, it makes it contiguous in DRAM, of course. Finally, something that I didn't mention in previous slides, but it's fairly obvious. We also must protect Sanctum from DMA devices from, so for example, you want to make sure that an operating system cannot configure your network card to steal private data from an enclave. And to do this, we've established a pair of machine mode registers that can be configured at boot to only whitelist a specific range of physical memory as something that can serve as DMA requests. we ask the operating system to allocate all DMA buffers in that range, and that range is included in the attestation and cannot be altered after the machine boots. This prevents any such attack. So in terms of elegance, I guess I should point this out since this is the RISC-V community. This work was incredibly easy because this chisel generator for Rocket Core is awesome. If you want to do any hardware hacking that looks anything like what we've done, this is great. And the only thing that turned out to be quite hacky indeed was the last level address bit rotation, which due to the way the last level cache is implemented in the Rocket generator turned out to be a little nasty. All of this is quite fast. We've measured, well, depending on the benchmarks you choose, of course, you can make this arbitrarily slow because giving private last level cache sets to an enclave effectively reduces the last level cache availability to a program. So if you choose something that requires a large last level cache to run, it will of course slow down when run inside of an enclave. But on average, we've observed somewhere between 1% and 6% overhead for a broad range of scientific benchmarks that are entirely inappropriate for secure processing. And yeah, I guess I should also include this mention that it's only about a 2% area increase because it boils down to just a few gates and a few configuration registers. So while Sanctum is not the end-all to computer security, because of course it's not, this small set of hardware changes to Rocket Chip does allow a small piece of firm ground upon which system designers can build secure systems. Because what this does is it allows you as a programmer to work with a very productive abstraction of a private process. As long as your application does not go outside of this private process, the enclave, and leak its own secrets by doing things like I/O, which the operating system can spy on, then your data is safe. A typical enclave should really look like just a decryption algorithm followed by your business logic, followed by re-encryption of the results. If you can structure your systems in such a way, then enclaves are a great match to do private remote computation with strong integrity guarantees. So I guess I should also mention how we obtain various performance results, which I will cover if time permits. But essentially, we just modified the spike simulator to keep a whole bunch of performance counters and event logs that are relevant to Sanctum events. We assigned a cost model that was informed by by essentially FPGA prototyping. And we ran the spec06 set of benchmarks compiled against RISC-V Linux with a whole bunch of custom headers, producing a log of cache events and a whole bunch of performance counters. We then plugged it into a custom last level cache model that I wrote that implements Sanctum's isolated LLC, which is not complicated by way of hardware, but it is a little tricky to model because we want to be able to model different sized enclaves simultaneously. And finally, we post-processed all of the above into a final committed instruction and cycle count, which is a proxy by which we measure performance. All in all, we simulated 275 billion or so instructions, which is a very large number. Sanctum, I'm sorry, the RISC-V chip, the Rocket chip is a very productive one against which to sort of do ballpark estimates of performance, because as an in-order pipeline, you can essentially separate out all the concerns that cause performance overheads and look at them individually. This is great. How much time do I have? Done. Okay, awesome. Well, great. Please ask me questions.
I'm sure there's questions. We'll have time for 2 or 3 questions.
You can also find me at the mixer or at a break, and I will answer all of your questions.
The one software exposed side channel that I didn't see anything on there is bandwidth things. Like if you have a process measuring memory bandwidth, it will notice when the secure cores are heavily accessing memory.
That's a very good observation. There's a few others also. We do not protect things like, so the on-chip network is one of them. DRAM bandwidth is another one. We don't protect those explicitly. We also failed to find any even like far-reaching, crazy academic work that attempts to actually extract any good signal-to-noise ratio and attacks targeting those. If you know otherwise, please let us know. The techniques we've considered in building Sanctum are not incompatible with protecting those channels as well. Essentially, you would have to over-engineer the network or the memory controller to guarantee quality of service to an enclave. there you would get the same kind of guarantees of isolation that you would for all of the other surfaces discussed. Thanks.
Alex Almakinko. So comparing your work to SGX, one of the problems with SGX is that these constraints on memory usage. Like you have to allocate certain percentage of memory for SGX enclaves up front. And you seem to go even further in this direction where you say not only memory, I'm also allocate the core, and it makes it like as somebody who had to deal a little bit with SGX, that was a big concern. And you seem to take it even to further to the extreme where you say, oh, okay, I'm actually dedicating a core per enclave. Well, that's kind of...
Yes, we absolutely double down on this isolation by resource commitment track that you don't seem to like. This is true. It is an elegant way to get isolation guarantees.
It's not I don't like. It's like big customers who don't like it. They
This is not a personal attack. I see. Yes, so there are more complex implementations that would give you finer grained isolation guarantees that we did not consider simply because this is an academic project that seeks to illustrate the idea that isolation is a really good way to do security. But yes, ultimately, simply because you are isolating an enclave from the rest of the world, you must create permanent resource allocations, and the hardware must enforce those. And there is some internal fragmentation that is a consequence of that. Perhaps we can learn to be more efficient in this by doing finer-grained allocations, or perhaps by just managing resources better. But this is a necessary consequence in the way I see the world.
I just want to say, comment that actually, one of your usages that you said something about cloud. That's exactly what people hate about.
Of course, and cloud providers do like to deduplicate things, which causes no end of security problems, but it is very good for billing. So actually, I do have one very quick comment on that front, is because we design enclaves to be very small, we don't intend to put an entire guest operating system or even a very large application into an enclave. So what you really want to do is create a small resource allocation to do just the logic that you care about, an X-ray analysis thing, or some machine learning, or perhaps some lookup in a private data structure. Those don't require a ton of resources, and those can only receive an allocation of a few last level cache sets, or perhaps a small amount of memory, which is easier to deal with than something like an entire guest OS.
Okay, one last question.
Yes,
Go ahead, Steve.
Steve Wallach. You mentioned that if you have access to the hardware, you may not be able to make all the security. Let's assume have the following scenario. Intel has the SGX or whatever. They ship millions of computers. I buy 1,000 of them. I put them in a shop where I have a whole bunch of people who understand computer design and have some of the most sophisticated test equipment that money can buy. And I like to use the term, conduct an experiment on all these 1,000 computers where I test to see the response to various attacks or whatever, and get a profile of how the system behaves. If I were to do that, would I be able to, would you still say it's secure or not?
Well, okay, so I guess taking that a step further, I could simply buy an ion beam microscope and steal a device secret from an Intel SGX chip, at which point I can construct an emulator, and until Intel revokes my keys that I stole from this chip, which is actually very tricky in the case of SGX, I can run this cloud service that defeats people's expectations of security. This is true. This is a necessary consequence of this remotely attested execution model. It's not perfect. It's good for some things. It essentially places a fixed cost on defeating a specific device. Buying a few thousand of these and building a profile of them is not enough to defeat an arbitrary device. It would only allow you to extract the secret keys from those specific devices and emulate those. We're relying on this manufacturer as certificate authority model to do proper revocation and things like that. And we don't have a cohesive story there because we're relying on the broader community that works with remotely attested execution to solve that problem.
As Eric Gross pointed out in his presentation, where he put on who the bad guys are. He had nation states, real nations, who have the capability, and others who don't, who look for low-hanging fruit. So, draw your own conclusion.
It's true. So far, as far as I can see it, companies have had pretty good incentive systems in place not to do malicious hardware designs. if they were to do so, they would of course be discovered at some point, and they would lose the credibility in their keys. This is something that would essentially tank their value, and we're hoping that manufacturer as CA model is sufficient to incentivize companies to build correct hardware. We have no story in place to fix things like manufacturers' supply chain attacks or malicious manufacturing, simply because hardware cannot be properly inspected and verified yet. If this is something that somebody else is going to have to solve one day.
Awesome. Thanks, Ilia.
Thanks, sir.